So today's video, we're going to discuss the bonds between molecules. It's going to be a review because we already made a video on hydrogen bonds, already made a video on van der Waals forces. So this is a review of bonds between molecules, and the first one, we're really not going to do very much with. It's called dipole-dipole attraction. Dipole-dipole attraction. We'll talk about that briefly. Probably the most important bond between molecules is this next one, hydrogen bonding. The next one is really a weird one. They shouldn't be sticking together at all. They need help to stick together. It's van der Waals forces. And the final one, the one we're going to start out with, is called molecule-ion attraction. So these are the four bonds between molecules, okay? And like I said, we'll get over all of them, and we're going to start with molecule-ion attraction first. So there are two names for this bond. The molecule-ion attraction, well, the molecule-ion attraction, well, the molecule is water. The V, very strong dipole, water, and ion comes from ionic bonds. The other name for this, it tells the same thing. It's called hydration of ions, which means you're putting water on an ionic compound. So this is molecule-ion attraction or hydration of ions. This is a fairly easy one. So we're going to take the most common stuff. We're going to take this, which is crystalline solid, high melting point. This is sodium chloride, or typical name is salt, NaCl. Now, we're going to take Na and Cl. We're going to put those two together. Don't forget, Na is in group 1. It's a pretty big atom, but group 1 got one valence electron and wants to lose it. If you lose a valence electron, you are a positive ion. And then chlorine is way the other side, way to the right of the periodic table, so it's smaller than sodium, but it gains an electron, so its ion is pretty big. So that's Cl minus. Now, this is what a crystal would kind of look like of salt. Now, this is a crystal of salt. Well, what are the big ones? Well, like I said, since chlorine gained one, that outside shell had to spread out because it gained a negative. And so these are Cl minus ions. Cl minus, Cl minus. And then, since sodium was big and it lost an electron, it got smaller, they're the smaller ones. Na plus, Na plus, Na plus. Okay, now this is a crystal of an ionic compound. Now, when you put it in water, water, if you recall, is a very strong polar molecule. Why? Because oxygen is really electronegative and it pulls hydrogen's electrons close to it. So oxygen is slightly negative, the hydrogens are slightly positive. So when you put water on an ionic compound, obviously the Na plus is going to attract the negative part of the water molecule. So it's going to look like this. That's what it looks like, so we're going to draw it like this. I'm not going to put the hydrogens on there. And then remember, the oxygen end is negative, 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 negative. So that's what that looks like. And then the Cl minus is going to attract the positive H's. So it's going to be like that. So it's going to be H, 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 H. So it's going to kind of look like that. And the H's are positive. And they look like that. So that is what molecule ion attraction looks like. Remember, the O from the water molecule will be attracted by the positive ions, and the H's will be attracted to the Cl minus ion. It'll look like that. And all this together, all this stuff on the board will look like this. So how can you tell if it's molecule ion attraction? Well, you have Na plus Cl minus, and then you just look for the AQ. The minute it says AQ, that's molecule ion attraction. So, or hydration of ions, and most, not all, but most ionic compounds, when you put them in water, they will break up just like this, and they will break up into ions. And remember, if you have free ions in a solution, it conducts electricity. So this is molecule ion attraction or hydration of ions. So that one's done. That's a pretty easy one. Once again, just look for the AQ and you got molecule ion attraction. Now, the next one we're going to do, like I said, we're not really going to talk about very much. It's called dipole-dipole attraction. And remember, if you forgot what a dipole was, a dipole is two non-metals put together. And they have a different electronegativity, such as like, well, HCl. And if I had HCl, well, you know that these are two non-metals, and chlorine pulls harder than hydrogen, so it's a polar molecule. And remember, polar molecules can be called dipoles, two poles, positive end, negative end. Now, this is not a very strong one, and dipole-dipole attraction is usually between medium and weak polar molecules, and it's a weak attraction. So hydrogen's positive, chlorine's negative, positive, negative, and here is where the dipole-dipole attraction would be, right there between the chlorine, negative chlorine, and the positive hydrogen, but it's really weak. Okay, so remember, just normal polar molecules usually have dipole-dipole attraction. But if it's not a normal polar molecule, if it's a strong polar molecule, then it's just not dipole-dipole attraction. And that's the next one we're going to go over. So the next bond we're going to go over is super important, and it's called this. It's called hydrogen bond. And basically in high school chemistry, there's only 3 molecules that are strong enough to have a hydrogen bond between the molecules. So, watch. They're already circled. If hydrogen is bonded to a small atomic radius, super high electronegative element, it forms a very, very strong polar molecule or a very, very strong dipole. So, NO and F. If hydrogen is bonded to O, I get this, H2O, very strong dipole. If it's bonded to N, I get NH3, strong dipole. And if H is bonded to F, I get HF, strong dipole. So, once again, for hydrogen bonding, it can only be between 3 strong dipoles. If it's water molecule, all the water molecules will attract due to hydrogen bonding. NH3, all the NH3 molecules will attract due to hydrogen bonding. HF, all the HFs will get stuck together by hydrogen bonding. So let's do this. Now, we have these 3 for hydrogen bonding. H2O, NH3, and HF. If you see any of those, they can bond by hydrogen bonds. Now remember, it's not the bond between the O and the H in the same molecule. It's bonds between the molecules. So I'm just going to do a stick figure to represent water and watch. So the O is extremely electronegative, so it's negative, negative, positive, 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 and then remember the hydrogen bond is not between the O and the H of the same atom, it's between the O and the H of different molecules. So here is a hydrogen bond between the O and the H there, and here's one between the O and the H there. Those dotted lines are bonds between the molecules. They're bonds between strong polar molecules like water molecules, and that's hydrogen bonding. Now the same would apply for NH3 molecules or HF molecules. Okay? Now, since those bonds are there, this gives, well, let's take water. This gives water certain properties. In order to boil water, you got to break the hydrogen bonds first. So, any liquid that has hydrogen bonding will have a very high boiling point. But if you put water in a glass of water, the water will very slowly evaporate because you got to break those bonds. So the 2 main properties of liquids held together by hydrogen bonds, high boiling point, but low vapor pressure. And remember, low vapor pressure means it takes a long time for the liquid to evaporate. All right? So that's what's happening with hydrogen bonding. And we already know what the graph looks like. We'll do this very quickly. We know going down any group, the weight gets bigger. So that means the boiling point's going to increase going down a group. But if it's group 16 with oxygen ahead of it, here's what happens. H2O, H2S, H2SE, and H2TE. Now, this is the normal way. As the substance gets bigger, it has a higher boiling point. So it should look like this. Just like that. But it doesn't, because H2O is a strong dipole, so its boiling point is way up here. So now it would go like this. So the boiling point of water is way up here due to hydrogen bonds. And then these H2S, H2SE, H2TE, they're weak polars. They don't have hydrogen bonds. Okay? So, and then this gives all sorts of crazy things like I said on the last video. Surface tension, water rolls up into a sphere because every water molecule is hooked to each other. I call it sticky. All right, so that's hydrogen bonding. And this could be not only H2O, this could be HF also, and going down group 17. It would look the same. Okay? That's a quick review of hydrogen bonding. I do have a video just on hydrogen bonding if you want to watch that. Now, the last one we're going to do is the weirdest name. van der Waals forces or London dispersion forces. I like van der Waals forces. So this one is very strange because this bond is super weak, but it's between things that shouldn't attract each other. Van der Waals forces is between nonpolar molecules. Now, you're thinking nonpolar, got no poles. So how can they attract? Well, when you take college chemistry, they'll explain to you about the electrons in a nonpolar molecule can just go back and forth and create little positive ends and little negative ends. But I'm not going to tell you that in high school chemistry. In high school chemistry, in order for nonpolar molecules to attract each other, they need help. So let's take an easy one. Let's take propane. Now remember, most nonpolar molecules are gases and there are some liquids. But you know about propane because you probably have a propane tank. So propane is this. And here's one. So the formula, I'm not going to put the H's up there. The formula for propane is C3H8. And if you look at that molecule, you'll see that it's symmetrical. If it's symmetrical, there's no poles. So propane is nonpolar molecule. They should not attract each other. So they need some help. Okay? And you've seen this. If you went with someone to get your tank of propane refilled, they fill it, and when you pick it up, it's really heavy. But when you shake it, there's a liquid in there. Propane is a gas. How in the world did they make propane a liquid? Remember I said nonpolars need help to stick together. Well, what they did is, if you have low temperature and high pressure, and you stop the molecules basically from moving around too much, and you put pressure on them and they get closer and closer and closer, finally they get close enough, but bam, the gas turns to a liquid. And that's what happens with the propane. It's under high pressure. And you know that's what happens because there's a liquid in there, but when you open up the valve, liquid doesn't come out, gas comes out. So that bond between the nonpolar molecules, which would be right here, that van der Waals forces, remember the molecules have to be super close, and it's a super weak bond. So the minute you release a little bit of the pressure, oh, that's gone, they're gone. So van der Waals is really, really a weak intermolecular force between nonpolar molecules. And think about nonpolar molecules. We're breathing two really good examples, O2 and N2, and we're exhaling a really good example, CO2. And you know with all of those, if you put high pressure, low temperature, we can change them to liquids. So for O2 and N2, you've heard of liquid nitrogen. Well, the only way that stays liquid if it's under some pressure but at tremendously low temperature. And then we have this one. We are exhaling CO2. CO2, symmetrical molecule, shouldn't attract each other. But when we put tremendous pressure on CO2 molecules and very low temperature, this is what happens. The CO2 gas turns into CO2 solid. I mean, gas to a solid. And you know that gas to a solid, it skipped the liquid state. And if you put CO2 solid, which is dry ice, in water or anything like that, you know that it doesn't melt. It goes from solid to gas. And it has to be a wickedly weak bond in order to go from solid to gas, and you know that CO2 sublimes. So CO2 sublimes from solid to gas. Now, super weak bond. So once again, van der Waals forces is the weak intermolecular force between nonpolar molecules. One more thing about van der Waals forces. What about this liquid? Well, remember, in this liquid, the bond is so weak that the boiling point is really low and it vaporizes very quickly. So in other words, it's got a really high vapor pressure. Think about gasoline. Gasoline is a liquid, and gasoline is this, C8H18. So it's pretty heavy. It's a liquid, but it doesn't want to stay together. So if you don't put a lid on a gasoline tank, it will evaporate because the bond is so weak holding the C8H18 molecules together. Now, a great example of van der Waals forces is going down any group. Going down any group, the size of the atoms get bigger, they're getting closer together, so going down any group, van der Waals forces increases. But there's a particular group that shows it perfectly, and it's group 17, and it's called the halogens. So, let's go back here. Now watch. Group 17, right here. We have fluorine gas. If it's a gas, the molecules are too far apart to have van der Waals forces between them. So, F2, no VDF. Cl2. Cl2 is a denser gas, but it's still a gas. The molecules are too far apart to attract, so no VDF. Br2, at room temperature, bromine's a liquid. Liquid, the molecules are very close together, so bromine has some van der Waals forces. Notice as we go down the group, what's happening. And finally, iodine. Iodine is a solid, okay? And if you're a solid, your molecules have to be touching. So, iodine has the greatest van der Waals forces, then bromine, and then nothing chlorine, nothing fluorine. So going down any group, as the molecular weight and the number of electrons increase, the van der Waals forces increases down a group. And group 17 is the best group to see that. All right? That is a very quick review. So I'm going to show you one more thing about van der Waals. So going down any group, van der Waals force increase due to the size and the number of electrons. If you had four substances, something like this, CH4, C3H8, C8H18, C25H52. If you had those four substances, and the question was, which one has the greatest van der Waals forces? You pick the one that weighs the most. It's just like going down a group, the weight gets bigger. So, the greatest van der Waals forces would be this one, because it weighs the most. If it said which has the least van der Waals forces, you pick the lightest one. Okay? That is a really quick review on bonds between molecules. If you have a problem, then I would go to the other videos that I made.